Everybody, welcome back to Smart Robots Review, the show that reviews robotics and other fantastic tech from around the world. I'm your host, Elias. It's great to have you here on my last day in Cape Canaveral, Florida, NASA Kennedy Space Center to cover the launch of the new Falcon 9 rocket. And this rocket is going to bring the new TESS satellite. This is a satellite that is going to hunt for new planets, exoplanets that could harbor life. So the launch is scheduled for 6:51 p.m. Eastern Time. My live cast on Smart Robots Review is going to start at 6:30. So join me then. I'm going to be talking about the rocket and the launch. It'll be a good time. We're going to have a great view. So I'm hoping to see you all guys there. JLC PCB is my sponsor for this video. Thank you guys for supporting me. Make sure you guys visit jlcpcb.com for prototyping and creating your own PCBs starting at only $2. So a great company. So now this video is very important. I have two scientists here, one from NASA, one from MIT. They're going to talk about the differences between TESS and Keppler. Enjoy.
Fantastic. Good morning. It's exciting. We've been planning TESS, the whole mission, for several years now, so this is really the culmination of an enormous amount of work to get this thing built and get ready to go into space. So what is TESS? It's a spacecraft that will be launched. It's about the size of a fridge. We're debating during our practice whether it's a washing machine or a fridge size, but maybe somewhere in between.
It's a small fridge.
It's an appliance size spacecraft, so it's quite small. And it's going to be going into, as mentioned before, a pretty special orbit. So it will take off from Kennedy, Cape Canaveral, tomorrow. It'll then go in through several orbits as discussed. But what's very exciting is it goes really relatively close to the moon, and it gets a really good kick from the moon. The moon's going to incline the orbit to our own Earth-Moon plane, and that's going to put it into its final orbit. The final orbit's an orbit of about 2 weeks. The spacecraft's going to orbit the Earth every 2 weeks.
Do you want to explain, though, what you mean by incline the orbit?
Yeah. So of course. The Moon and the Earth orbit each other. They're flat, about the same plane as the Sun. Our own whole solar system's in about the same plane. TESS is going to go around not in that plane. It's going to go around like this rather than flat. So whilst it's going around, it's going to spend most of its time fairly far from the Earth, and then come in relatively close to the Earth to download all its data. So, why do we do this? One of the questions was, why do we look for 27 days? 27 days is a nice balance. You can find a whole bunch of planets, but at the poles you can look for a lot longer than 27 days. You actually look for about a year at the poles and 27 days at the higher closest to the ecliptic. And I'm going to show them a movie now. This is showing you how we observe. Here's the field of view. So each of these tracks here is actually about the size of, if you were looking at this stage behind me, this is about the right size of kind of panorama image using 4 cameras. And each of these cameras is about 500,000 times bigger than the field of view of Hubble. These are really huge cameras we're looking at. And then we're going to move them around, looking at the sky, trying to find planets. Now you'll remember Keppler. Keppler was NASA's first dedicated exoplanet mission. How is it different? Jenn here is going to talk about some of the differences here.
Yeah, thanks. So TESS and the scientists who are working with her are in this really fortunate position where we get to stand on the shoulders of an amazing mission like Keppler. Now the main difference with TESS, as Martin mentioned earlier, is this desire to look at our closest and brightest stars, kind of our stellar neighbors, if you will. So if we can roll my first video, please. This is going to show you, starting off, the Keppler field of view, what we looked at for 4 years. There we go. So that's the constellation of Cygnus, and then the cross that shows up here is what Keppler stared at. And then on top of that, that's one of the TESS cameras. It's about the size of Orion on the night sky. Now each 27-day sector is comprised of 4 cameras making this vertical strip. And then what TESS is going to do is tile those strips, starting first in the southern hemisphere, as you see moving across the bottom of the screen. There we go. And then it'll switch to the north after its first year. And over those first 2 years, its primary mission, it'll cover 85% of the sky. Now by looking at such a large section of the sky, this kind of stellar real estate, we open up the ability to cherry pick the best stars for doing follow-up science. On average, the stars that TESS observes will be 30 to 100 times brighter and 10 times closer than the stars that Keppler focused on. Now what that means in terms of detecting planets is that our planetary census is going to move in. I hope we can pull up my second video, but just leave it on the first screen for a second. Perfect. So this is going to be an animation that will show you, zooming out, the planets that we found already. The ones found by Keppler will show up in blue. Planets found by other missions will show up in gray. And then planets that we think TESS is going to find using a variety of very well-designed simulations will show up in orange. So what's happening here is we're looking down on the plane of our solar system. And then if we can start the video, please. We're going to zoom out. So the first circle is 3 light years, next one is 10. You can see that within 30 or so light years, we already have some orange points. And as we zoom out further and further, you'll see that the screen is just covered in these orange dots, these predicted TESS planets. And eventually we see the contributions of Keppler and other missions come in, kind of stretching much further at the 100 or 1,000 light year level. But that central area that TESS is dedicating to is really where I think the majority of great exoplanet science and characterization is going to happen over the next couple decades. Because the planets that TESS finds will be orbiting stars bright enough to use things like ground-based telescopes to do radial velocity work, which is how we get masses of planets. When we combine those masses with the radii that TESS provides, we can start talking about things like planetary composition and what they're made out of, like Jesse mentioned earlier. And then for the very best and brightest and most promising candidates, future missions like the James Webb Space Telescope, which should launch in 2020, will be able to stare at those planets and peer into their atmospheres, looking for evidence of the atoms and molecules that we think might be crucial for letting life develop on those worlds. So TESS is really the next step in all sorts of goals for NASA, and we're really excited to see what science comes out of it.